elemental contents by PXR if
we have we have
PhD Thaís, we can hear you and we can see you.
Hi, let me ask you a question. Can I put the slide bigger, or I don't know if...
That's the size of the slide, so you cannot put it bigger.
Oh, okay, that's no problem. I think that, okay. Can I start?
Yes, please.
Good morning, everyone. First of all, I would like to say that it's such an honor to be here presenting some of my work. Unfortunately, I couldn't be in Mexico this year, but it's amazing to be participating in the Congress and to be presenting. The title of my work is Influence of Soil Properties on Elemental Contents Obtained by Portable X-ray Fluorescence Spectrometer, the PXRF. So introducing myself, my name is Thaís. I'm an undergraduate student in agronomy in Federal University of Lavras in Brazil. This is my advisor, Sergio Henrique. The PXRF is a proximal sensor that is capable of identifying and quantify the total content of numerous elements in different matrices. So as you can see in the picture, it seems like a pistol, and you can put this on any surface. If you have a rock or even if a table, almost any surface, you can put a trigger, and in this screen, you can see in about 30 or 60 seconds the concentration of numerous elements that has on this surface. So the concentration shows in percentage or in parts per million. Worldwide, this equipment has been used for pedological, agronomic, and environmental purpose. Okay. No, está bien. No te preocupes. Gracias. But how the X-ray fluorescence works? So when the X-ray reaches the surface of the soil particle, the electrons are the inner electrons are displaced to the outer shell. Like we have the X-ray, and sorry. The electrons that is on the inner shell are displaced to the outer shell. When this happens, there is an energy that's released in the form of fluorescence. Each element has its own fluorescence, has own characteristic spectral signature, and that's when we can identify which element is. And the intensity of the energy is proportional to the element concentration in the material. So that's why we can quantify the concentration of this element. So in this image, I can try to show how this works a little bit better. So here, imagine we have the soil particle. In the X-rays incident, when the incident X-rays reach the surface, this electron that is here in this green one, it's ejected. And when this happens, another one on the outer shell comes to fill this vacancy. So when this happens, the energy is strong. But the PXRF has some limits of detection. This one, we can, in the periodical table, we can see that this equipment can identify the elements from the magnesium until uranium, and all these elements that is between them, we can identify. But why do we study the PXRF, and why do we want to use that? The traditional chemical analysis in soil requires time and use a lot of chemical reagents, and it's considered not environmentally friendly. But the PXRF is an equipment that is really fast, as I said before, we can have the result in 30 or 60 seconds. It's considering an equipment non-destructive to the samples, so it allows us to reuse those samples. It's considering environmentally friendly because it does not require any kind of chemical, and requires minimal or no sample preparation. What helps us because we can use this on field. But there are some studies that shows that some soil properties can affect the results of the PXRF, such as moisture, texture, and organic matter. The soil moisture can observe or disperse the incident X-rays. This can influence in the final results because it can underestimate the concentration of the element. The texture. It's expected that the thinner and more homogeneous material have a better result. And the texture on the soil will have different size of particles, so it might interfere in the results in the end. The soil organic matter can attenuate the X-ray beams, so it can act, such as the moisture, it can decrease the contents of the elements in the final result. So the objects of this work was to create and evaluate the predictive models of aluminum, iron, and silicon. Wait a minute. Okay. I can't see the screen anymore. Okay, no, it's fine. What we want in this work is to use the PXRF in field and try to convert these concentrations into a lab results. So the hypothesis of this work is that the moisture, the texture, and the organic matter may help in the correction of the PXRF obtained in field, in being possible to convert them into the PXRF results in lab without requiring another analysis in lab. So here is some information about this area. So the samples were collected here in Lavras. The climate here is considered subtropical with dry winter and rainy summer. For the sampling, we collected and analyzed the main horizons for the main horizons of the profiles. We have 5 different parent materials and different soil classes, totalizing 59 samples. So how we did this work? So first of all, we defined the soil profiles, we separate the horizons, and in field, we took the PXRF. In each horizon, we made an analysis. After that, we collected all the samples of each horizon, took to the laboratory. Then we determined the soil moisture, the soil texture, and the soil organic matter. After that, we dried the samples and passed to a 2 millimeters sheaf. So we have the sample dry and more homogeneous. And after that, we analyze again with the PXRF. Then we developed the models and validated them. The soil analysis we made in triplicated 3 times during 6 seconds in the dual soil mode. In the laboratory, we determined the moisture, the soil texture, and the soil organic matter. So for each element, we create a linear regression model with different combinations with independent variables. Here we can see the I is the content of each element to be predicted in the air drying fine earth, is the one in lab, and the X is the content of each element obtained in the field. So here in the first one, we have only one equation with only the result of the analysis in lab and in field. The second one, we only used one auxiliary variable. Here we have moisture, texture, and organic matter. And the second and the third one, we have true combinations of the 3 variables. In the first equation, we have the combination of the three variables. For each element, we validated using the live-on-now cross-validation, and we calculated the square R, the root mean square of zero, the normalized root mean square of zero, and the relative improvement. The squared R, we want this to be high, so can say that it's more, the higher the square R is, the more explanatory the model is. The lower the normalized root mean square of zero is, the more accurate the model is. And the relative improvement, if we have proximal, then 100%, we can say that some variables helped us to make the model better. Here in this image, I can show you how the difference between the analysis in field and the analysis in lab. The darker bars are the one that we made in the field. You can see that concentration of each element is lower than the other bars, because the other bars were dried and passed through a 2 millimeters sheave, so it's more homogeneous and dry. So this is the square R adjusted for the model. For the aluminum, we doesn't have much difference between the variables. We only can see that when we add the organic matter, there's a little difference, a little decrease in the square R. In iron, we can see almost nothing in difference, but in silicon, we can see when we add the texture on the model, we can see that the higher is the square R. In the validation, we can see that the R square for the iron is really high, and the normalized square of zero is low. So we can say that it's a good model. It can perform as well. And the silicon, we can see that the same models with texture are higher, the square R, and the normalized root mean square of zero are low. So we can say that the performance is good too. In this table, I can show you the relative improvement. For aluminum, almost all the numbers are negative, so it doesn't have a lot of difference. The iron have a slight difference when we add the moisture and the texture with the organic matter, but it's a minimal difference. But when we see the silicon, we can see clearly a difference between the models when we put the texture. So we have 20.29, 22.29. So this can show something. In conclusion, the models generated for aluminum, iron, and silicon are demonstrated by the R square R adjusted. Aluminum and silicon models were mainly influenced by texture and moisture, since the water content and soil particle size influenced in the PXRF results. For iron, there's no significant change between the models, so it's possible to use the PXRF in field without the addition of cover radius, like the organic matter, moisture, and texture, in order to minimize time and make them more economical. In general conclusion, using auxiliary data such texture, moisture, and organic matter content in the equation, it is possible to observe improvements in the model. So that's the acknowledgements. This is the article that is based on. I would like to say, if anyone have any questions or any interest in the subject, you can text me, and I can recommend some different articles about the proximal sensors and talk a little bit. So thank you, everyone, and that's it.
have any questions to Thaís? Elizabeth Soyeiro.
Thank you very much for this presentation. I have a question regarding the, I forgot the word, not the accuracy, but I don't know, the validation of the equipment, because these items, portable items, are not so good in relation to the big equipment, to X-ray fluorescence. So did you calibrate the equipment in order to get more accuracy in the results?
Yes, we have the NIST, that is the sample that we calibrate in each beginning of each analysis. I don't remember the name specifically, but it's the NIST. We have the sample that we can calibrate, and in each beginning of the analysis we use this one. So after that we make we make the calculus to accurate. I'm sorry. Me perdonas que no sé cómo hablar eso en inglés. Perdóname. Pero sí. Pero sí
It's okay. It's okay. Another question?
Didn't
Dr. Katz?
I can send you after.
Thank you for your excellent study. I think this is something which will in future be used much more. Now, we have done a little bit of studies as well, and our experience was that you need a homogeneous structure and a very plain surface in the profile, and also the bulk density is of influence. And you use texture, moisture and organic matter, and only later you came to the structure and the bulk density.
I don't know if I understand really well. Can you hear me?
To answer if it's difficult.
I think I didn't understand you. Sorry.
Yes, that the structure is also another element that you have to be you have to consider in order to improve the model.
Yes. This one is actually this PXRF. We are studying a lot here. I think here in Texas Tech we have a lot of work on that, and we are trying to improve every time more. So it's kind of the beginning. I think it started here in my university about 3 years, and we are trying to improve with everything now, have some work with plans and everything, so we can understand a little bit more and how we can improve those models. This one is just one word that I was working on. But thank you.
Thank you, Thaís. Well, we are going to proceed to our next speaker. And please.